Welcome everyone. For today's prep, we're going to start looking at our basic derivative rules. So far we've looked at the conceptual beginnings of what the derivative actually is. So slope of the tangent line, instantaneous velocity, and we saw how the derivative, where it really comes from, is that limit of a difference quotient. That's our definition. So we had our limit definition. Well, it turns out that there's rules that kind of help us calculate the derivative so that we don't have to go back to that limit definition every single time. And we're going to start looking at these basic rules. And to kind of get started, we're going to look at two little examples. We're going to look at the linear function. So a function in the form mx plus b. So the graph of such a function is a line. And we want to think of the derivative as telling us what the slope of the curve is at any point on our function. So if we graph this function, mx plus b, if we look at any point on this function, well, this function is just a line. So the slope of our curve at any one of these points is always going to be the same. It's always going to be m. So when we have a function like this, mx plus b, the derivative is just equal to m. So that's a linear function, this specific format. Well, kind of even more of a special case is what happens if we have our function equal to b, a constant b. Well, in this case, our derivative is a constant function, so it's just flat. It's horizontal like this. So the derivative of this, again, we want to think of this as the derivative is telling us what the slope of the curve is. So when we have a flat line like this, at any point on here, the slope of our curve is 0. So the derivative is equal to 0. So we have kind of these two special cases. We have linear functions and constant functions. Well, what happens if we kind of increase the power function? So right now this is just x to the power 1. What happens if we have a bigger power or a different power, something other than x to the power 1? Well, our first major rule, and we're really going to use this one, is called the power rule. So this tells us how to differentiate when we have something x raised to the power r. And the way this works is you want to think of this almost as like a process. That's the way I kind of think of it. So our first step is, step 1 is to bring down the old exponent. So we have this power function that we're going to differentiate. We're going to take that old exponent and we're going to bring it down and put it in front of the x. So that's our first step here. We're bringing down that old exponent, put it in front. Then the second step is we keep our variable exactly the same. So our variable is x in the original function. We're going to keep our variable x in the derivative that we're going to get. So we keep the derivative exactly the same. And then our last step for this power rule is we're going to subtract 1 from the exponent. So we take our old exponent, which was r, and we're going to subtract 1. So this is our power rule. So let's try an example. Let's keep this rule in mind, and let's look at part 1 of example 1. We're going to differentiate this function x squared. All right, so let's try it out. So we're going to do our derivative here. So we're going to calculate and see what f prime is. So what are we going to do? First step, we're going to take that old exponent, and we're going to bring it down and put it in front. So we're going to bring down the 2. Put it in front. Then we keep x the same. We keep our variable the same. So that's the second step there. We keep our variable the same. So we don't always use x. Sometimes we might use like t. So you just keep the same variable, whatever you got. And then our last step is we subtract 1 from the old exponent. So our old exponent was 2, and we subtract 1 from that. And if we clean this up, we end up with 2 times x raised to the power 1, and we don't normally write raised to the power 1. So Once you get the hang of this, you're probably not going to show this step. Perfectly fine if you want to, but once you get the hang of this, you don't have to show this, the 2 minus 1 in this case. Sometimes if our exponents are a little more complicated, it actually doesn't hurt to show this, but for integer ones like this, it's not normally necessary. All right, so let's try another one. Let's look at x cubed. So again, we're going to do the derivative. We're going to use our power rule. So our function is f of x, so we're going to call this derivative f prime. And we're going to do the power rule again. So what do we got? Our function here is x cubed, so it's x raised to a power. So we're going to take that old exponent, bring it down, put it in front. So our 3 goes in front. Then we keep the variable exactly the same. So our function here had an x. Our derivative is going to have an x. So we keep that the same. And then we're going to subtract 1 from the exponent. So our old exponent was 3. If we subtract 1 from that, we're going to get 2. And this is, realistically, when you do these, you can probably go right from the function right to the derivative. One step. All right, so let's look at the next one, square root x. Now this is a little bit different. This isn't immediately written as a power function. So our first step before we do any derivatives is we got to rewrite this as a power function. So rather than the square root of x, we're going to rewrite this as x raised to the 1/2. So we got to rewrite the root function. And we're going to see these quite a bit. So in general, if we have the nth root of something, we can rewrite that as raised to the power 1 over n. So if our little root sign had like a little 3 here, then we would put 1 over 3. The square root's kind of special. Technically, we could put a little 2 here, but we don't normally do that. So technically, there's like a little 2 there. But if we had the 4th root, well, then it would be 1 over 4. If it was the 5th root, well, then it would be x to the 1 over 5. So this is going to be something that we see. Having the root function kind of looks nice, and it's easier to understand what's going on. But being able to differentiate is going to be easier with this written as a power function. So once we get it written as a power function, now we're ready to do our derivative. So our function here, again, is called f of x. So we're going to calculate, we'll call our derivative f prime, give it a nice name. And now we're looking at this. So we're going to take this old exponent, we're going to bring it down, put it in front. So we're going to bring that 1/2 right down in front. We keep our variable the same, so it's going to stay x. And this is where, once we get to like fractional exponents, at least at first, it doesn't hurt to actually write that -1 step. So we take our old exponent, which was 1/2, and we're going to subtract 1. And if we do 1/2 minus 1, again, if you want to do this off to the side, doesn't hurt. So you could think of this as 1/2 minus 1 is equal to 1/2 minus 2 over 2, which is -1/2. So sometimes with these fractional exponents, you might want to do a little bit of thinking off to the side there. So this ends up simplifying to just -1/2. So our derivative here is 1/2 x to the -1/2. All right. And let's do one more. Another kind of special case one. This is the function 1 over x. So when we have a fraction like this, and let me just kind of rewrite this just to emphasize that we do have a fraction here. This is 1 over x. This is going to be kind of another special case. We want to write this with a negative exponent. So when we see an x term in the denominator like this, and a constant up in the numerator, we want to rewrite this fraction using a negative exponent. So the way to do that is, technically this is like x raised to the power 1 down here. So that's like x raised to the power 1. And actually, let me throw that in. So all we do when we rewrite this with a negative exponent is we're going to get rid of the fraction. We're going to keep the exponent that was there, but then we make it negative. So the exponent 1 was there, so we're keeping that, and then we just make that negative. So if this was like 1 over x squared, we would do x raised to the, we'd do a 2, and then just make that negative. So it'd be x raised to the negative 2. If this was 1 over x cubed, well, we'd keep the 3 and then just make it negative. So it'd be x to the minus 3. And then once we get it like this is the preferred format because this is a power function. It's x raised to a power. So now we're ready to do our derivative. And we'll call our derivative, again, f prime. And the first step is we take that old exponent, and we're going to bring it down, throw it in front of the x. So we'll have our negative 1 down there in front. We keep x the same, and then we take that old exponent and we subtract 1. So again, if you want to do it, you can. So we take our old exponent and then we subtract 1. So if you want to show this step, perfectly fine, at least at first here while we're still learning this. And if we simplify, this ends up being negative x raised to the minus 2. And not absolutely necessary. Actually, this format might be good if we want to do like a second derivative. But sometimes it's helpful to write this back as a fraction. If we wanted to like plug a number in or evaluate this, sometimes it's helpful to write this back as a fraction. And we could do that by let's keep the negative. Let's keep that negative 1, that negative 1. We're going to put that in the numerator. And then we're going to take this x raised to the minus 2, and we're going to get rid of the negative in the exponent, and we're going to make it back into a fraction. So this would be x squared. So we're getting rid of that negative, and then it throws the x squared down into the denominator there. So sometimes this is helpful to rewrite it like this. Again, not absolutely necessary, but it can be helpful. Same thing with going back to our square root one here. Once we get our derivative, this version here is perfectly fine. It'll be good if we want to do a second derivative. But if we want to start evaluating, it might actually be easier to convert this back to a root function. And actually, with this negative 1/2 here, we would use make it into a fraction as well. So, we could rewrite this one as 1/2 times 1 over x raised to the 1/2. So again, we're taking this power function and we get rid of the negative in the exponent by just doing the reciprocal. So we take the x raised to the 1/2 and we just do the reciprocal, and that gets rid of the negative in our exponent. And then we could get rid of this x raised to the 1/2 by just rewriting it just like we did in our first step here. So another way to rewrite this would be 1 over 2 times square root x. So, like I said, you don't always have to do this. Perfectly fine to just leave it like this. A lot of cases this is preferred. But if we want to evaluate, getting it back into this form is actually sometimes a little bit nicer. All right, so in class, where we're going with this is we're going to see how can we combine different functions. And so we're going to be looking at constant multiple rule. So that'll tell us how to differentiate when we have a constant that's multiplying our function. So we'll see how to do things like this, where we have a power function with a constant in front. And then we'll also be looking at the sum and difference rules. So that tells us what happens if we have addition or subtraction in our function. So we'll be looking at, where we have power functions with addition or subtraction. So we're going to be trying those out. So we'll see you then. Bye-bye.